Um, what we're talking about today and a week from now is a very, very cool site. And I want to start by showing you something that could look kind of weird to most people. Essentially, um, this is a crew of workers carrying a 200 feet long device and slowly installing it, sliding it into the ground through one of these many stainless steel casings you see installed here. These go at least 120 feet below grade, and some of them as far as 200 feet underneath the building. And this is all done custom in order to treat a TCE source area, which is located between 50 and 120 feet below grade, below a building where we couldn't get access. So the first webinar we'll be talking about how did we design and install a system that could actually remediate TCE that deep underneath an area where we don't have access. And the second webinar next week, we will talk about what data comes out of that. How do you know how it's going? How do you know when you're finished? And how can you convince the regulators that you are? So that will be a week from today. But today we have two wonderful panelists. We have Scott Tarman from Ramble, and we have Bob Glass from TRS. And I'd like to kick it off by starting to ask you, Scott, to give us a little bit of a background about the site and the objectives of this project.
Sure, Gorm. Thank you, everyone. So this is a Superfund site in northern New Jersey with US EPA oversight. The site is divided into three operable units, or OUs, OU1 and OU2 and OU3. And OU1 and OU2 are basically down gradient. It's an area that's considered where the dissolve phase CVOC impacts are. It's situated in the Pohatcong Valley in northern New Jersey. And OU3 is the subject where the source soil contaminations are where the source originated from. And that is the area that we're focusing on in today's webinar. But that area is an area where there is an active manufacturing facility. It's about a 294,000 square foot facility. And as Gorm mentioned, the impacts mainly reside at a depth of 50 to 120 feet directly beneath the center portion of that facility. So the US EPA selected remedy for OU3 included the implementation of thermal treatment to address the deep TCE soil contamination. And in situ thermal remediation by means of thermal conduction heating technology was selected to address those TCE impacts, and namely to achieve a remedial goal of 1 milligram per kilogram of TCE. I'd like to just draw your attention really quick to that center area within the building, that red box. That is an area that's about 125 feet by 180 feet. And that room is essentially the area where most of the work had to be conducted from within inside the building. So it's about approximately a little less than 1/10 the size of the building footprint size. Mm-hmm. So what made this project so unique is there were just numerous regulatory, operational, scheduling, and technical challenges that were needed to be overcome. And from the regulatory perspective, being a Superfund remedial action under US EPA Region 2 oversight called for a heightened level of communication. The project also is being driven by a consent decree with stipulated penalties and the threat of potential takeover by US EPA if certain milestones weren't achieved. And of course, the low remedial goal of 1 milligram per kilogram TCE in the soils needing to be achieved. But operational challenges relative to the active manufacturing facility, there were just drilling the drilling limitations and site logistics forced the need to perform installation completely within the manufacturing building. And as a result, there was just potential for significant business interruptions, and consideration needed to be given to limit those interruptions and impact on facility operations. And additionally, the site is actually operating as they make packaged beauty products and various hygienic products there, and it required that the interior be hygienically clean, some of those production areas inside. So that made it extremely challenging. And then just the time frames.
It's a certified clean facility, right, Scott?
Certified, yes, that's correct. Certified clean facility. Thank you, Bob.
Yes, there are numerous. And if you look at where that red box is, there's no access to that location from the exterior. So every time we accessed our work area, we had to go through their facility, and it was, logistically challenging.
Yep, that's right. So with regard to timeframes, the consent decree had very aggressive timelines to complete the remedial action. And then because the work was mostly conducted inside the building, there were significant cost impacts to our clients associated with occupying that interior room. So there was that area had to be leased out for the period of remediation. But really, the challenges here that we're going to talk about and some of the really interesting aspects are relating to those the technical challenges and how we've successfully overcame a lot of the issues relating to just the location and the geometry of the subsurface impact, spatial constraints, drilling at limits of the equipment capabilities, identifying additional volume for treatment, and also verifying the placement of the constructed heaters, just due to the sheer length and depth of those. So, and then lastly, of course, maintaining just a safe work environment throughout the construction presented many challenges.
Fantastic. Of course, the first step in any type of remediation, definitely a thermal remediation, is to figure out where the blob is that you're treating. And Bob, maybe I can ask you to cover that, basically the target treatment zone and our conceptual approach for treatment. And when I do that, we're focusing in on this red area where we had access, and then the source area, which turned out to be bigger than that, right?
Sure. I think we have a slide that shows a more zoomed in portion. Yeah, there it is. All right. So yeah, first step in any one of these remediation projects is identifying the problem. And kudos to Scott and his team. Ramble did a very extensive pre-design investigation. We came into this job with way more information than we typically would have when we're designing a system, and that was fantastic. What you're seeing here was, kind of our first crack at what we thought the treatment volume or treatment area would look like. There's high resolution data here that we were able to design around, which was fantastic. This picture on the right is interesting. That's out of an EVS model, and we're going to revisit this later in the webinar and show how we used the real data that we got post-installation to tweak the system and help optimize during operations. Scott already alluded to the fact that the goal here was 1 milligram per kilogram. So when they were doing that investigation, that's what they were looking for, right? Anything in exceedance of that 1 milligram per kilogram. Something that was interesting was during that installation, when we first started on what we thought was the blob, we were actually able to collect more data. And subsequently, we're able to reduce that footprint a little bit on either end, which was fantastic, right? That's less infrastructure that we have to install. It's less energy that we have to use. It results in a cost savings for the client. So, we kept learning as we moved beyond the design phase and into the installation phase, which I think was super efficient for us. In total, that thermal treatment zone, it was 37,000 square feet. but that equated to about 27,000 cubic yards, so fairly large site. And what's unique about this site is that a large portion of that plume, actually the majority of the plume, was in an inaccessible area. So on that left figure, you see where it says Group B and Group A. Those areas are under an active portion of the facility where we could not access. So we had to figure out how to fit all of our infrastructure into this blue box and access areas that were hundreds of feet away and like 100 feet below grade. So very challenging. You saying something, Gorm?
Yeah, well, just wondering, just so these dots up here, these are heater locations, right? And the green are also heaters, but at the angled heaters you installed underneath the clean rooms. And just to show what we're looking at, the green blob here is the TCE that exceeded 1 milligram per kilogram, right? Real quick question, why don't we treat all the way to the surface?
It's a great question. So yeah, in general, the treatment interval rather started at 60 feet below grade. So it's common on TCH sites that the heaters will go all the way to the surface if you have contamination up there. We didn't, right? And it started very deep. So if we had heated all the way to the surface, you can see that green blob, right? That's what we're targeting. Everything above was clean. And if we had heaters going all the way to the surface, it would have posed numerous issues, both financial and technical, for us on this job. One, it would be a ton of energy, right? Because we would be losing energy in these heaters, and we'll look at what a heater is here in another slide. But we would be losing a ton of energy and wasting a ton of money heating an area that is not a target for us.
Yeah.
The other thing is, it's an active building, right? So if we're heating up to the surface, there's a potential for vapor intrusion in the form of steam into the building. And, we do heat up to basically below grade in buildings on other projects, but it requires additional infrastructure and monitoring and all these things that weren't really necessary here. So significant cost savings to start it down at 60 versus coming to grade.
Okay, fantastic. One last question on this, and then we'll move on to Scott. Why group A, B, and C, just in a few seconds?
Yeah. So Scott already alluded to the fact that we were under a very aggressive timeline here. This project also took place from 2019 to 2022. So we were smack dab in the middle of COVID. And in order to meet that aggressive timeline, we devised a plan to do it in stages so that we could install one group and then start building the surface infrastructure for that group while we were drilling another group. Subsequently operate the first group that we built while the other one was being built. And at one point in time, we had one group operating, one group drilling, and one group building all at the same time. So cool. Yeah, logistically challenging, but it worked out well. Very,
very cool. So it turns out to be about 172 total heaters. Just saying these red sticks, that's the heated interval, and at the top of every one of them, there's an SVE point to extract the steam and the vapors. Just for those of you looking at this and wondering, what is that? All those red sticks. I'll go to you, Scott, and ask you to briefly talk about the restrictions in the building and some of the challenges it takes when you're installing this, and how do you do it, and how do you do it with the building and ceiling right above you and obstructions?
Sure. So a really important element of the design phase was being able to, determine that the system could be constructed, and the proposed heater layout that was designed with the EVS model that's being showed previously. We had to make sure that, obviously you needed to get in there with drill rigs and be able to complete those heater casings at their locations. So low overhead clearance presented, and also the presence of structural impediments such as building columns, and then also there are overhead utilities, air ducting, various things of that nature throughout the interior room. And what we ended up doing is we ended up doing design evaluation that used a 3D point cloud survey to identify interferences, prior to mobilizing for drilling. The ceiling clearance was only about 14 feet, and with the presence of the ventilation ductwork and overhead utilities, made clearance in some of the other areas much less. So the 3D point cloud survey was used using LiDAR, and the survey essentially helped us look at where those locations could be done, and plan for the use of up to 4 drill rigs within that room. As shown on the left most picture here, you can see there's one of the angled drill rigs that was being used. You can see that the clearance, overhead clearance restrictions that were imposed. And on the right-hand side is an illustration of the 3D LiDAR, the point cloud survey. And you can see what we ended up doing is the block in the middle is used to represent the angled drill rig. And this was laid out in AutoCAD, where we could just move that block around and be able to look at each individual heater well location to make sure that it could be installed at that location. And if there was areas where it couldn't be installed, then we had to go back and readjust some of our heater locations and design until we were able to make sure that it could be successfully drilled as specified.
And this was so critical, right? I mean, you're looking at 1 drill rig out of 4 on the left there, and they were different, right? So this was a long mast rig. We needed to bring this in to do these really steep angles, right? So they had to take that into account. And then we had a short mast rig that looked like this that could do shallower angles, but it was limited to angles. And then we had 2 different kind of drill rigs that could do the vertical ones and some angles. And, without understanding where the pinch points were, we would have definitely struggled. And even so, I mean, you can see the clearance we were dealing with. It was very tight, very, very tight.
So what's this here, Bob, on the left side of the drill rig? What's weird attachment?
Yes, that was the bane of my existence for a few months. That is the exhaust. So you could envision 4 mini sonic rigs operating in essentially a big warehouse at the same time. They're producing lots of exhaust, lots of heat. We needed to manage that. Obviously, we can't exhaust that just out into the open, right? So we had to construct a fairly complex exhaust system with a stack and a blower, with temperature monitoring and vapor monitoring to make sure we weren't having any indoor air issues. We also had just a tremendous amount of noise, frankly, being produced from these rigs. So there was definitely worker safety complications there. Actually, a cool thing we did, we were kind of like Top Gun pilots. We bought these ear protection devices that were basically radios as well. So one of the challenges when all of this is going on is just communication. I mean, you can't talk to anybody while these rigs are running. So we got these little radio systems and with multiple channels. So each drill crew had their own channel, and you could walk up and switch over and talk to them and see how things are going. That ended up being one of the better things we purchased for this job.
I know another really cool thing Scott purchased for this job, the DeviFlex tool. Scott, maybe you can tell us a little bit about that and why it was needed.
Certainly. So for starters, what I'd like to just talk about is, the onset of drilling. Thank you, Gorm. The onset of drilling, it was really necessary to install the heater casings accurately and to verify the constructed angled heaters, were within tolerance limits specified by the design. So state-of-the-art surveying equipment was used to accurately align the drill rig when setting up on the angled heaters. So we used a portable surface alignment tool called a Devi aligner, which is a true north seeking gyroscope alignment tool. And as shown on the photo on the left is shows how that was used. This little black box set up on the drill casing is the W aligner, and that was used to essentially align the first flight of drill string as it was being advanced, and we'd go back and do continuous checks on that for the first two to three drill strings as after they were advanced, just to make sure that we were on the proper trajectory and alignment. So that tool was really, really important to making sure that our target zones would be hit. But then after completion of each angled heater well, the casing was surveyed with a specialized survey tool called the DeviFlex. And that tool measures the direction and inclination of the borehole as the survey equipment is lowered down the casing. That enabled the calculation of trajectory coordinates to determine the deflection over the length of the heater casing. And that's shown on the illustrated photo on the right-hand side, where they're actually lowering the tool. That survey tool is about 13 feet long. So you're just really only seeing the top portion of it there. But it was connected to a winch system, and it was lowered down in 10-foot increments where it would then record the coordinates. And then it was retrieved. It was surveyed going down, and then also survey coordinates were taken as it was being retrieved. So we'd have two sets of survey coordinates to compare to each other. And then most importantly is that the survey coordinates were used then to put into the 3D EVS model to allow for real-time evaluation of that angled heater well casing with respect to the target treatment zone. So really at the spacing between heaters, we targeted not to exceed 22 feet, which is really based on experience from past TCH sites. But when the deviations caused larger gaps, the real-time adjustments were made to the angle and the azimuths of the yet-to-be-installed heaters to make up the difference. Or in some instances, we would install additional heaters to make up for some of those larger gaps due to deflection.
And the deflection was a major thing in the beginning too. This was a glacial till for the majority of the treatment volume. So it's very surprising to me that, a 6-inch sonic drill casing can do a corkscrew over the length of approximately 200 feet, but it did. And we learned so much from this tool that without it, we'd be just guessing if we were where we needed to be. And maybe we can flip over and look at, the output of this data.
We can. Yes, we can.
Yeah.
This model?
Yeah. Yeah. So this is ultimately what we made with the data that Scott's talking about, right? And this is how we made decisions based on, do we need to adjust the entrance point or the angle of an additional heater based on what the one we just previously installed did. So you can flip this all around 360 degrees and identify those gaps in the coverage and then make adjustments. So this was a daily exercise for us, looking at did we nail it or did we move a little bit, and what can we do to fix it? A very, very powerful tool. And you guys that will attend our next webinar will see more of this and hear about how we used it day to day in operations. But yeah, very, very critical tool.
So one of the things we could do is kind of take a virtual swim down right here and see what's the distance between these two. These are two heaters, as like Scott said, 22 feet or so. It's like, okay, we better install another one in between because this area will not get hot enough. We simply can't sample everywhere. So we needed to know that our heater coverage and all our hot rods would basically cook the whole thing, right? Because we couldn't take data everywhere. Did you mention how many additional heaters we needed based on this survey, Scott?
We needed a total of 7 additional heaters, Gorm. which really wasn't too bad considering 178 total heaters. Not too bad.
Cool. Very good. So I'm going to flip back to you, Bob, and ask you to just explain very quickly the conceptual model and the approach, how we actually got the TCE out.
Sure. So what you're looking at is a heater, basically. So what we were just discussing installing, that's the casing, right? And what goes inside the casing is basically a resistive element that gets extremely hot, upwards of 1,000 degrees Celsius. That heat radiates away from that heater and essentially boils off the contaminant. That gets put into a vapor phase, right? We're volatilizing it. So we need to capture that vapor. So as Gorm alluded to, we had co-located vapor recovery screens that were under a constant low vacuum to sweep that steam and that contaminant up into our treatment system. And basically when those heat fronts converge, right, with one another, you have full treatment. And that's thermal in 10 seconds. It's a little more complicated, but basically it's a big.
So essentially, I just want to remind everyone out there, you can ask questions in the Q&A box. I should have said that earlier. You can do it anytime, but in about 5 minutes, we'll go and read those questions. But just fire them in there, and if I can get to them earlier, we will. So we have about 3 questions at the moment, but you're more than welcome to ask more under Q&A. And now we're going to start rounding off the introduction or the webinar here by just talking about some of the logistics, some of the things, and we're going to move up above grade, up here where you see the heater stick up, and there you can see vapor extraction piping. How did we manage to install all this inside this relatively small room for the relative big remediation? So it's open to both of you to help explain these. We have 4 or 5 pictures here to show everyone what happened.
So Bob, why don't you go ahead and take that one?
Yeah, sure. I spent a lot of time in these boxes. So what you're looking at here is a heater head, is what we call it. Basically, it's the top of the picture we were just looking at, right? And you can see that each one is at a very specific angle, right? So these are lined up in what we would call a heater fan. It's part of our strategy to be able to have multiple different angles with one entry point. The box on top is connected with these electrical cables back to breaker panels and ultimately back to our power source. And that's how we would regulate power to individual heaters. There's a cable that stretches down typically, down to 60 feet below grade, but on the angles it was longer, and that connects to your heated element, right? It's hard to see, but next to the heater boxes is a smaller stainless tube. That's our vapor recovery screen. And that feeds into the larger stainless steel header you can see in the back and ultimately to our process treatment. But there's some other pictures, I think, that show that a little better.
And those of you who were here from the beginning of the webinar, the video I showed is essentially how we put the long heater element into one of these. We slid it into this 200 feet long hole in the ground, if you will.
There were lots of installation challenges here at the surface. You can see we did a lot of overhead routing, right? There were lots of things to take into consideration, right? We needed ingress and egress into the work area. We needed to honor arc flash boundaries for all of the boxes, as well as all of the panels and the various equipment. And those arc flash boundaries are variable. So that was something we had to consider. These stainless steel headers are very hot, right? That's how we're collecting our steam. So they can't be touching electrical cables, for example. So a whole host of logistical challenges and thought and design went into what you see here, ultimately making it a workable space in a relatively small area.
Mm-hmm. And
so Bob, you mentioned that a pathway needed to be kept across the interior room. That pathway was for the facility operations because the central location of this room relative to the building and their operations, it was critical that they maintain a thoroughfare through there so they could get equipment through and materials through. So that even made it more of a premium for space inside the interior room to place the equipment. But because that center pathway across the interior room addressed the center of the room, we ended up having to put a lot of the piping and cables, routing them outside onto the roof to minimize that disruption and also to free up space inside. So here is a figure that shows where a lot of those cables and piping that was shown in those previous photos went up onto the roof, and we went across, and then where the outside equipment was located, treatment equipment, just made opening up that area so much more easy and allowed us to essentially avoid a lot of issues.
Yeah, and our process equipment that you're seeing here, I mean, that has to be outside, right? We've got cooling towers and generators and blowers, all sorts of things that can't be inside. Even if we had the space, we wouldn't have been able to do it, right? So the roof, going across the roof ended up being the most direct path, I guess, or the easiest path for us, but came with a host of challenges all its own, right? We had a lot of infrastructure there. So
Yep. Fantastic. Thank you, guys. I'm going to start reading some of the questions that have come in. Turn off the screen sharing. One person, Michael, asked if we considered horizontal directional drilling to steer the wells for their entire distance.
that's a great question. It's not a conversation that I engaged in, but if you have suggestions on contractors that can do that, I am all ears, because that would be, yeah, it's something that we've considered for other jobs. For this one, I don't know, the process that we went through to land where we did, but because of all of the discrete angles, I think
and I can shed some light. I can shed some light on it. So when we first were scoping this work out, we did look at trying to access the contaminated target treatment zone from the exterior of the building, essentially because of where that treatment area was with respect to the outside of the building. It would have increased the length of drilling by, would have doubled it, at least doubled it for some of those areas just to get down into the center portion of that building. So that would have made drilling a lot more challenging just from a equipment limitation reason. But moreover, even on the outside of the building, there were access restrictions. On the south side of the building, it was very tight. The property boundary isn't much more than about 75 feet on the south side of the building. And on the west side, that was used for mostly parking, employee parking. And space was really a premium out there. So that really led us only to one option, and that was doing it from the inside of the building and doing angle drilling from within.
Yeah, and it was about 4.5 miles of casing that we put into the ground. So when we're talking about doubling it, it was a considerable effort just to get the 4.5 miles in. It took about 1.5 years.
Yeah. Very good. Frank Baranko has a really good question. I think we forgot to mention. He said something like, I'm rephrasing it now, how can the TCE's blob start at 50, 60 feet? What happened up above? And Scott, if you can just briefly explain.
Sure. So we did high resolution site characterization where we had taken soil samples on 2-foot spacing intervals, numerous borings throughout that area where we had access in the building within that central treatment area. Some areas where we could get access in the production room, we also were able to get down with some vertical boreholes, but not very many of them. But we were able to identify through that high resolution site characterization data that the upper 50 feet of that soil, it wasn't absent of TCE, but it had concentrations that were below our target remedial goal of 1 milligram per kilogram. So therefore, they weren't subject to treatment. So it's not to say that they wasn't there, but where we started running into contamination in excess of our remedial goal started at a depth of 50 feet and it went down to about 120 feet.
Yep. A couple of quick questions I can address. The volume treated was 27,000 cubic yards. We had to heat closer to 40,000 cubic yards because if, as you know, those EVS blobs are not smooth, they have basically weird shapes. So in order to ensure that all 27,000 cubic yards were treated, we had to heat roughly 40,000 cubic yards. Yeah. Another question was the angles, let's say, how shallow of an angle did we go? And I think that's around 30 degrees from
30, yeah.
Right, Bob?
We had one at 29 if we want to be technical.
Yeah, yeah.
Yeah.
The record one. And in order to drill at such an angle, how do you do that? Why doesn't the drill rig just move back when you're trying to push?
Yeah, we had to anchor them down. So at a specific angle, I can't remember exactly what it was, so I'm not going to throw it out there, but maybe 45, something like that. We would end up having to set very large anchor bolts and actually wrench the rigs down so that they would stay in place. But there were other problems to it. Those really steep angles and the long ones, we would notice mass deflection. So we actually had to fabricate supports and things for the rigs that were doing the very long ones to make sure that the mass wasn't deflecting. And it was a host of challenges at those angles.
So I know that, there was also something that made it very difficult to drill. Had we had a large diameter hole, it would have required so much force that drilling would be impossible. Let's say we had a full-size sonic rig or something, we would not have been able to have big enough machinery in there, right? Can you explain how we minimized the borehole diameter and therefore could get by with a mini sonic system?
Well, I think it really comes down to what rig can fit in the building and what is the maximum size of the tooling it can use, right? So we made some design changes in order to reduce that borehole size, and that was specific to our heater casing, right? It allowed us to use smaller tooling and subsequently smaller rigs. So that was one thing that we did.
Mm-hmm.
Yeah, and I could add to that. Just TRS's design on their heaters. What Gorm showed at the beginning of the webinar, that allowed the heater casings to be installed that were only 2.5 inches in diameter. Yeah. So you really didn't need to have that large of a casing. So that was really paramount to a lot of the drilling success out here. It wasn't a large borehole. So that also saved a lot in terms of drill cuttings and costs for disposing of drill cuttings as well.
Yeah. And just a reminder, there was 14-foot clearance, right? There was a question on that. Maybe someone didn't hear the beginning of the webinar.
Generally 14 feet, but there's a lot of infrastructure that was along that roof that was not removed and left in place. But because they did that 3D analysis, we knew we would be able to get the rig in, but there was much lower clearance at certain areas. So you have to take that into account when you're setting up your angles and your verticals as well.
Yeah. At the end of all this, do we have to remove the casings?
So they were abandoned in accordance with NJDEP regulations, and in New Jersey, you're able to abandon in place. So we did cut them down below grade. We grouted them in, cut them down below grade. All the void space was grouted, and then we resurfaced that concrete in the areas that we had disturbed it. So.
Excellent. So when we're inside an active facility, what other precautions do we have to take? I'm thinking about, and Lauren is asking about noise, temperature, vibration, indoor air. How was this project different than say an outdoor TCE project in that respect?
You
want to take that one, Scott?
Sure. So yeah, that's a great question. So we ended up looking at vibration as an issue out here, and also noise, just because of the nature of the facility, being active with operations with pretty sensitive equipment inside their production areas. We ended up doing vibration surveys to making sure that there was, just it was kept within reasonable amount of vibration. So we did have survey monitors going on throughout the operation just to make sure that there were no issues there. And then secondly, with respect to the noise, at the onset of the project, that interior room was actually on one side of it was actually open. In other words, it didn't have all four walls surrounding that room. So we ended up having to construct a demising wall to essentially seal that off from noise being disturbing all the operations going on inside the facility and workers. So that was an added thing that needed to be done to account for some of those issues and to protect the workers in the facility.
And we also worked on second shift during drilling, right? So the loudest, most annoying part, I guess, if you're a worker there, was conducted at night, so that we were minimizing that impact.
Right, and then it also we had to dig quite a bit into the industrial hygiene too on this, just due to the the welding of the steel casings. There was a lot of indoor air monitoring that was being done to look at making sure there weren't any welding fumes, worker exposure to welding fumes, and various things like that. So we were continuously monitoring that throughout the operations and doing testing just to make sure that the workers were indeed being protected.
Yeah. I want to share my screen again one last time, because there is a question from Tanner. Again, I'm rephrasing a little bit. He says, with this long, so the vapor extraction screen is this dotted portion. That's where we apply a vacuum to the formation and suck out the TCE vapors and steam generated. He's asking, wouldn't condensation be an issue in this, and how was that managed?
That is a great question, and a difficult one, because it can be an issue, right? It's something we dealt with on this project. So yeah, as soon as that steam starts to get cool, right, and it's going through that cool section, there's an amount of it that will start to condense, right? And then basically what would happen is it will condense, it will roll back down into the heated area, and then it's going to flash again and come back in. So eventually you're removing so much water that your steam production goes down, your condensate production goes down. But it's absolutely something we dealt with. So and part of we had equipment in the room to help us deal with it even further, right? So it gets out of the ground, now it's in the room, it's continuing to condense in the piping before it ultimately gets to our condenser where we want that to happen. So we had to put in something called a vapor liquid separator with a pump, more or less, to basically be a stopping point along the way for all of that condensate to accumulate, and then we would pump that out over the roof, like you saw, and ultimately to our condensers for further treatment. Something we dealt with, yep, for sure.
Another really good question in there is, one is asking, does this work below the water table as well?
Sure. Yeah, thermal works great below the water table. This particular brand of thermal, if you will, thermal conduction heating, is very sensitive to water. So if you have like high groundwater flow, it's not that thermal conduction heating won't work, it's that you need to manage that via hydraulic control. So and Gorm, you can speak to this more eloquently than I can. I mean, you can definitely use it in those situations, but there might be other thermal technologies that are more appropriate.
Yeah, essentially thermal conduction heating and electrical resistance heating is, at most our sites, is used both above and below the water table at the same time. If at this site we had to treat below the water table as well, we would have had different challenges, because we have bedrock down there, and you can imagine it's hard enough to drill with Minisonic 200 feet down at an angle and hit a rock, and then you have a deflection of the drill casing, right? And Scott gets busy with his Viviflex tool. But if you're trying to penetrate bedrock down there, it would have been even more difficult. So that would have been a drilling challenge. But technically, yes, if we were below the water table and there was more heat capacity, we would have had to have a tighter spacing between the TCH casings. So it would have looked quite different, but luckily we didn't have to. This was a Beto-zone remedy. There is just an amazing, convenient question from Nick, and I'm going to use that as the final question of the webinar and thank both of you for your participation. Nick is asking, is there enough space in the work area to drill and collect performance soil samples to figure out when you've met your objectives? What do we say to that?
We say tune in to the next webinar to learn more. Well, go ahead, Scott.
Yeah, no, so if you recall, we talked about that central corridor or room, that pathway that went through our central room. So what we ended up doing was we ended up going back, and we were able to use that pathway through that central corridor in that area to install hot soil sampling and put in borings. So granted, it was very helpful to do that, but it limited the number of samples and drill holes that we were able to install. So like Bob said, that'll be a topic of the next webinar, but yes, we were able to put in 4 boreholes in there, and because there were some areas within the production facility that had walk pathways, that walkways and things like that, we were able to get some of the smaller drill rigs in to do 2 locations inside the main production area.
Over here, right?
That's correct. Yep.
This is the corridor that was open for foot traffic and for small drill rigs to do confirmatory sampling. And next week we will have 2 other smart people. We will have Bruce Kennington and Scott Thomas, and they will talk about all the challenges of proving that we are actually remediating the site with the limited data we can actually get. You can see the soil locations. It's not a whole lot. Typically for an area this size, almost an acre, we would have maybe 10 or 20 boreholes, and we would have multiple soil samples from each one to show that we're done. Next week, at the same time, we'll talk about the multiple lines of evidence that it took for us to ensure that we actually met the goals. So we hope that most of you tune in again next week, and hopefully talk to you then. Thank you so much.
Thank you.
Thanks, everybody.